In section 4.5, we look at exponential and logarithmic equations. This is the most important section of the chapter. First, let's talk about the one-to-one property of exponential functions. If you have an equation a to the x power equals a to the y power, the only way this can be true is if x is equal to y. We can use this to solve some simple equations. So for example, consider the equation 2 to the t power is equal to 128. Now to solve this, you need to know that 128 is 2 to the 7th power. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, and 64 times 2 is 128. This is 2 to the 7th power. So we have the equation 2 to the t equals 128. We can rewrite this as 2 to the t equals 2 to the 7. And because of the one-to-one function property, since the base on each side of the equation is 2, we know that t must be equal to 7. Let me give you a slightly more interesting example. Consider the equation 9 to the x plus 2 equals 27 to the x minus 1. As it sits right now, we cannot use this property because these bases are different. However, we do know that 9 is equal to 3 to the 2nd power, and 27 is equal to 3 to the 3rd power. So we can rewrite this equation as 3 to the 2nd power quantity to the x plus 2 is equal to, on the other side, we have 3 to the 3rd power quantity to the x minus 1. And now we can use the property of exponents. A to the m power to the n power is equal to a to the m times n power. And so what we have here is 3 to the 2 multiplied by x plus 2 power. And on the other side, we have 3 to the 3 multiplied by x minus 1 power. And now, because we have a common base of 3, we can set these powers equal to each other. So we know that 2 times x plus 2 must be equal to 3 times x minus 1. And this means 2x plus 4 must be equal to 3x minus 3. And if you solve for x here, you will get x equals 7. Next, let's talk about steps for solving exponential equations. This is a more general strategy. So step 1 is to isolate the exponential expression on one side of the equation. Step 2 is to take a logarithm of both sides with respect to a suitable base, and we will talk about this, what that means. Then use the power property of logarithms to write the equation without the exponent, and then solve the resulting equation. So in our first example, we have 10 to the power 2x minus 1 equals 3 to the power x. Now, what I want you to notice is that the bases are different. 10 and 3 are not the same, and we cannot make them the same because 10 is not a known power of 3. So what we're going to do in this problem is first isolate the exponential expression on one side of the equation. Well, notice that there are two exponential expressions, one on the left side and one on the right side. So what we're going to do is take a logarithm of both sides with respect to a suitable base. Now, when solving logarithmic equations, there are really only two bases that you will be using. You will either be using a logarithm, which of course means log base 10, or you will use a natural log, which means log base e. Now in this problem, because there is a base 10 on one side, I'm going to use a logarithm base 10. So if I take log base 10 of the left side, we get log of 10 to the power 2x minus 1 equals, if I take the log of the right side, we get log of 3 to the power x. Now the reason we do this is because once you have the log of something to a power, the power that is here can be brought down in front of the logarithm. We can do this on both sides. So on the left-hand side, we get 2x minus 1, that whole thing, multiplied by the log of 10. And on the right side, we get x multiplied by log of 3. Now, let's remember that log of 10 is equal to 1. So this becomes 2x minus 1, right? Because if log of 10 equals 1, 2x minus 1 multiplied by 1 is 2x minus 1. And on the other side, we have x times the log of 3. Now what we're going to do is gather all of our variable terms to one side of the equation. So what I'm going to do here is add 1 to both sides to get the 1 over there, and I'm going to subtract x log of 3 from both sides. This gives us 2x minus x log of 3 is equal to 1. Now the reason I do that is because now I have an x in both terms here, and that can be factored out. So we can say x multiplied by 2 minus log of 3 equals 1. And finally, dividing both sides by 2 minus log of 3, we get x equals 1 divided by 2 minus the log of 3. Now, this is the exact answer. And we always want to give the exact answer. But we should also give a 4 decimal place approximation. So you can plug this into your calculator, and we get the following. And so what we get here is approximately 0.6567. And this is the answer rounded to 4 decimal places, which is the typical number of decimal places. Now remember, this is supposed to be the solution to the equation, which means if you take this answer and you plug it into the original equation at the top, you should get approximately the same thing on both sides. Let's check our answer to make sure that it's right. So here's our original equation. We're going to take this value of x here, we're going to plug it in on both sides. And when we do that, we get 10 to the power 2 times 0.6567 minus 1 should be approximately equal to 3 to the power 0.6567. So we can plug both of these into a calculator. So on the left-hand side, we have 10 to the power 0.3134. And on the right-hand side, we have 3 to the power 0.6567. And now if I plug each of these into the calculator separately, we should see that they are approximately equal. And indeed, you can verify that although these answers are not exactly the same, they are very, very close to the same answer. Now, why they are not exactly the same is because, remember, we didn't plug in our exact answer. We plugged in a 4 decimal place approximation to that answer. And anytime you use an approximation, there is a little bit of error involved. In our next example, we have 3e to the 2t plus 6 equals 24. The first thing we want to do is isolate the exponential expression. So I'm going to subtract 6 from both sides. This gives us 3e to the 2t is equal to 18. And then I can further isolate the exponential by dividing both sides by 3. And when we do this, we get e to the 2t is equal to 6. Now for this one, notice that we have an e involved in the problem. So what we want to do here is take a logarithm base e of both sides, and that is, of course, a natural log. So we have the natural log of e to the 2t must be equal to the natural log of 6. And again, the reason we take a logarithm is because now we can use the property of exponents, or the exponent property of logarithms, to bring that exponent down. And when we do that, we get 2t times the natural log of e is equal to the natural log of 6. But again, we know the natural log of e is 1, because remember, natural log of e means log base e of e. And this is equal to 1 because e to the first power is equal to e, right? So natural log of e is 1. And since it's equal to 1, this is just 2t multiplied by 1, which is 2t. And on the other side, we have the natural log of 6. And finally, to solve for t, we divide both sides by 2. And we get t is equal to the natural log of 6 divided by 2. And again, this is our exact answer. And you can plug this into a calculator to get a 4 decimal place approximation. And that 4 decimal place approximation is t is approximately equal to 0.8959. And remember, you can always plug that number in to make sure your answer is correct. And I recommend checking your answers. But I think I will skip it here. In the next example, we have a special type of exponential equation. It's one that is in quadratic form. So you'll notice that the structure looks a little different. Now, the key thing to remember here is that if you have e to the x and you square it, this would be e to the 2 times x. So in this equation, e to the 2x minus 2 times e to the x minus 3 equals 0, we can rewrite e to the 2x as e to the x quantity squared. And then we have minus 2 times e to the x minus 3 equals 0. And I'm only putting the parentheses here for effect so that you can see that what you have here is the same thing. Now, what I can do is make a substitution. I can let u equal e to the x. And if I do that, we end up getting u squared minus 2u minus 3 equals 0. And notice that this is a simple quadratic equation. We can solve this by factoring. We have u minus 3 times u plus 1. And then we can set each factor equal to 0. And we get either u equals 3 or u equals negative 1. Now you have to remember that we're not actually solving for u. U is something that we created to make the equation look simpler. So once I get the solution for u, I need to remember that u is really e to the x. So I'm going to put e to the x in here. And that gives us e to the x is equal to 3 or e to the x is equal to negative 1. Now, to solve these equations, what we need to do is simply take a natural log of both sides. So in the first equation, we get natural log of e to the x equals natural log of 3. This allows us to bring the x down in front, and we get x times the natural log of e. Remember that natural log of e equals 1, so that's just x equals the natural log of 3. This is one possible solution. And for the other solution, if you take the natural log of both sides, I want you to notice that you get the natural log of e to the x equals the natural log of negative 1. But the natural log of negative 1 does not exist. You cannot take the natural log of a negative number. So this solution here, or this equation rather, has no solution. So the only answer to the question here, or the solution to the equation here, is x equals the natural log of 3. Let's take a look at an application. Suppose a bank pays interest at a rate of 5% compounded continuously on an initial deposit of $1,000. How long does it take for an investment of $1,000 to grow to a total of $1,200, assuming that no withdrawals or additional deposits are made? Round your answer to 2 decimal places. So remember, for continuously compounded interest, the amount in the account is equal to the principal balance times e to the r times t. R is the interest rate, t is time. And in this problem, we know the interest rate is 5%, which we can rewrite as 0.05. We know the principal balance is $1,000. And we know the amount that we want to have in the account at some future time is $1,200. So we're going to take all these quantities and plug them into the formula. So on the left-hand side, we have A, which is 1,200. On the right-hand side, we have P, which is 1,000, multiplied by E to the power 0.05 times T. So again, I'm just taking each of these numbers and plugging them into their respective variables. So now we're solving an exponential equation. So what we want to do is isolate the exponential expression. I can do that by dividing both sides by 1,000. If we do that on the left-hand side, 1,200 divided by 1,000 is 1.2. And on the right-hand side, we get e to the 0.05 times t. Now that we have the exponential isolated, we're going to take a natural log of the left side, and that would have to be equal to a natural log of the right side. Now, the reason we picked natural log is because we have a e in this problem, right? And we know that the natural log of e is 1. So when we bring this power here down in front, we end up getting the natural log of 1.2 equals 0.05t times the natural log of e. But again, the natural log of e is 1. So this gives us the natural log of 1.2 equals 0.05t. And finally, dividing both sides by 0.05, we end up getting an exact answer of t equals natural log of 1.2 divided by 0.05. And if you plug this into a calculator, you get the following. And if you round that to 2 decimal places, we get t is approximately equal to 3.65. Now remember, this is in years. So it will take approximately 3.65 years for $1,000 to grow to $1,200 at an interest rate of 5%. This next example is very similar to the last example. Suppose a colony of bacteria doubles its initial population of 10,000 in 10 hours. Assume the function that models this growth is given by P of t equals P naught times e to the kt, where t is given in hours and P naught is the initial population. So first it says, find the population at time t equals 0. So what they're asking for here is, what is P of 0? Well, P of 0 is P naught times e to the k times 0, right? All I'm doing is I'm plugging in t equals 0 here. Well, this is P naught times e to the 0, right? Because k times 0 is 0. And e to the 0 is 1. So this is P naught times 1, which is P naught. So its initial population, P naught, is 10,000. They told us that. In the second part, they ask us to find the value of k. How fast is it growing? Well, they do tell us that the population grows from an initial population of 10,000 and it doubles in 10 hours. So this means that the population in 10 hours is 20,000. But we also know that the population in 10 hours should be given by 10,000 multiplied by e to the 10k. So what I'm doing here is I'm plugging in t equals 10, and p naught is 10,000. And so we know that these are equal to each other, so 20,000 must be equal to 10,000 times e to the 10k. And now we just need to solve for k. So I divide both sides by 10,000 to isolate the exponential. These cancel out. 20,000 divided by 10,000 is 2. So we get 2 is equal to e to the 10k. We take the natural log of the left side and the natural log of the right side. And this allows us to take this power now and bring it down in front of the logarithm. And when we do that, we get the natural log of 2 is equal to 10k times the natural log of e. Again, we know the natural log of e is 1. So this is the natural log of 2 is equal to 10k. And finally, dividing by 10, we get k is equal to the natural log of 2 divided by 10. And we can plug that into a calculator. And when we do that, we get k is approximately equal to, let's do 4 decimal places. I can say 0.0693. And let's keep in mind that this means 6.93%. So that means that the growth rate of this bacteria is 6.93% per hour. Now, the final thing they ask us is to find the population when t equals 20. Now, we can do this a couple of different ways. The first method would involve just using your original formula. So we know that P of t is equal to P naught, which is 10,000, multiplied by e to the kt, but we know that k is 0.0693. And if I want P of 20, I'll just plug 20 in. So we get 10,000 e to the 0.0693 multiplied by 20. And I can plug this into a calculator to get an approximate answer. As you can see when we do this, if we round this to the nearest whole number of bacteria, this is approximately 39,988. However, there's actually an easier way to get this answer. They told us in the beginning that the population doubles every 10 hours. So if you think about it, if we start with 10,000 bacteria, in 10 hours, we're going to have double that amount, which is 20,000 bacteria. In another 10 hours, we're going to have double that amount, and double 20,000 is 40,000. But 10 hours plus 10 hours is 20 hours, right? So how many bacteria should you expect to have in 20 hours? Well, you would expect to have 40,000 bacteria. Now, I want to point out that the answer that we got down here is very close to 40,000, right? But we could have easily gotten an answer of 40,000 by just recognizing that since it doubles every 10 hours, and they asked us how much bacteria would be there in 20 hours, that we just basically need to double 10,000 2 times. Now, of course, the reason this answer is approximate was because our value of k here was approximate. And since we have an approximate value of k here, when you use that approximate value to find other values, those values will also be approximate. Next, we talk about steps for solving a logarithmic equation. And the steps are sort of similar. First, we want to isolate the logarithmic expression on one side of the equation, and then we want to exponentiate both sides with respect to a suitable base, and then use the inverse relationship between exponents and logarithms to write an equation without the logarithm, and finally solve the resulting equation. So let's talk about these steps in regards to this first example. we're solving the equation 4 plus log base 3 of x is equal to 6. And I'm first going to start by isolating the logarithmic expression. And I can do this by subtracting 4 from both sides of the equation. And this gives us log base 3 of x is equal to 2. Now from here, what they say to do is to exponentiate both sides with respect to a suitable base. So that means we're going to take the base of the logarithm, which is 3, and we're going to say 3 to this power equals 3 to this power. That's what they mean by exponentiate both sides of the equation. So we're choosing the base of 3 because there's a base 3 in the logarithm. So we know that if we take 3 and raise it to the log base 3 of x, that this should be equal to 3 raised to the second power. Now, why do we do this? Well, it's because when you raise 3 to the log base 3 of something, these cancel each other out. And so you just end up with x there. And of course, on the other side, 3 squared is 9. So we have our solution. Now, there is another way to do it that they don't talk about in the textbook, but I want to show you here. So another approach when you get to this step is to simply use the definition of a logarithm. So we know that when you have log base 3 of x is equal to 2, that by definition this means 3 to the second power must be equal to x. And you can see that that also gives us the same solution. Now, if I'm being honest with you, I prefer doing this, but I'm going to stick with the way that the book does it, and occasionally I'll show you both methods. At any rate, the answer here is x equals 9. In our next example, it's a little bit more complicated because we have a log of 2x plus a log of x plus 4 equals 1. And so our first step here is going to be to simplify by combining these logarithms. And we can do that by using a property of logarithms that we talked about in the last section. So we can combine these together by saying log of 2x multiplied by x plus 4. Now keep in mind that this is a base 10 logarithm, so we can combine these because they're both base 10. And that's equal to 1. Now again, because this is a base 10 logarithm, what I'm going to do is take the number 10 and raise it to the power log base 10 of 2x times x plus 4. And on the other side, I'll take the number 10 and I'll raise it to the thing on the right side, which is 1. Now you don't have to put the 10 in the log base 10, right? So if you want, you can take that out. We should all know that that's a base 10 logarithm. But the point here is that 10 to the log of something, right? Because that's log base 10, those cancel out. And we just get 2x times x plus 4 is equal to 10 to the 1, which is 10. And now from here we can distribute on the left-hand side. And we can subtract 10 from both sides because we have a quadratic equation. And then we can factor out a 2. And then we can finish the factoring using our factoring techniques that we've been discussing in this class. And from there, we can set each of those factors equal to 0. Not the 2, of course, just the x plus 5 and also the x minus 1. And here we get x equals negative 5. And here we get x equals positive 1. Now, when you're solving a log equation, you need to check your answer because, remember, you cannot take the log of a negative. So notice that you cannot have an answer of negative 5 because if you plug that in, 2 times negative 5 is negative 10, right? So when you check here, if x equals negative 5, you have the log of 2 times negative 5 plus the log of negative 5 plus 4. equals 1, and this is not true because this is log of negative 10 plus log of negative 1 is equal to 1, and these do not exist, right? You cannot take the log of a negative number. So x equals negative 5 is not a solution. And then we can check x equals 1. So same thing, plug in x equals 1. And to the left-hand side, we get log of 2 times 1 plus log of 1 plus 4 is equal to 1. This says the log of 2 plus the log of 5 is equal to 1. Well, we know that this is the log of 2 times 5, right? Properties of logarithms. And that is the log of 10 is equal to 1. And that is true. So x equals 1 is our only solution here. Now, if you allow me for a minute to just go back to this step in the problem, this is where you exponentiate both sides using a base 10 because you have a log base 10. I prefer to do it a different way, and I'm just going to remind you of how I like to do this because I know that some students prefer it. So right here at this step, what I prefer to do here is to remember that this is a base 10 logarithm and use the definition of a logarithm to tell us that 10 to the first power is equal to this. So 10 to the first power equals 2x times x plus 4. And that, of course, gives us the same equation that we solved a minute ago here. So the rest of it would be the same, but this step, using this definition as opposed to exponentiating, that's an alternative way to solve the problem. In the next example, we have the natural log of x is equal to 2 plus the natural log of x minus 1. So what I'm going to do first is get my natural logs together. I'm going to subtract a natural log of x minus 1. From both sides. This gives us natural log of x minus natural log of x minus 1 equals 2. And the reason for doing this is because now that I have these together, I can combine these by taking the natural log of the quotient x divided by x minus 1 equals 2. Now again, the way the book describes this is because you have a base e logarithm here, you're going to take the number e and you're going to raise the number e to the power that appears on both sides of the equation. So e to the natural log of x over x minus 1 must be equal to e squared. The reason for doing this is these cancel. And from there we get x over x minus 1 equals e squared. And don't plug that into a calculator, just leave it as e squared. We can write that as e squared over 1, and then we can cross multiply. So x times 1 is x. And then here we have e squared times x minus 1. And this is x equals e squared times x minus e squared when you distribute here. And now what I can do, most people would probably just subtract this over here. I'm going to bring this x over here, and I'm going to add the e squared over there. So I'm going to add e squared to both sides. And I'm going to subtract x from both sides. And in doing that, we get e squared is equal to e squared x minus x, right? These cancel out and these cancel out. And now, since I have an x here and an x here, I can factor out the x. So we have e squared equals x times e squared minus 1. And now finally we can solve for x by dividing both sides by e squared minus 1. And we get x is equal to e squared divided by e squared minus 1. Now again, I'm just going to remind you that, the book likes to do it this way. I like a different approach. What I would normally do right here is just remind myself that a natural log is a base E logarithm. And then I can use the definition of a logarithm to say that e to the second power must be equal to x over x minus 1. And that's just another way to get to this part of the problem. So you can use whichever method you like. I just want to show you both. Before we go on to our last official example, I want to look at one more example. So in this problem, we have log base 2 of x plus 5 equals log base 2 of x plus log base 2 of x minus 3. Notice that every term has a log base 2. So first what I can do is I can combine these together using properties of logarithms. So we have log base 2 of x plus 5. And on the right side, we can combine these into log base 2 of x multiplied by x minus 3. Now, the way the book would explain to do this is because you have log base 2, you would raise 2 to the power that you see on both sides there. So 2 to the log base 2 of x plus 5 is equal to 2 to the log base 2 of x times x minus 3. And the whole point here is that 2 to the log base 2 cancels, and you get x plus 5 is equal to x times x minus 3. And from there we can solve, this is just a quadratic equation. So we have x squared minus 3x equals x plus 5. Subtract x and subtract 5 to set this equal to 0. And we get 0 equals x squared minus 4x minus 5. And from there we can factor. And when you set these factors equal to 0, you get x equals 5 or x equals negative 1. Now, when you check your answers, of course, you cannot plug in negative 1 because you cannot take the log of a negative there. So we're going to get rid of that answer. You can plug in 5. Notice that when you plug in 5, you get 5 plus 5 is 10. Here you just get 5, and 5 take away 3 is 2. So there's no trouble with plugging in 5. So 5 is our answer. Now, one last thing I want to talk about, of course, is at this step right here. The book would have you do it this way, as I've been mentioning. But we can actually do this in a much simpler way. And it just involves the fact that if you have a log base a of one thing, and it equals a log base a of another thing, you can simply drop the logs on both sides. So you can go directly to the step x plus 5 must be equal to x times x minus 3. So I'm not using the definition of a logarithm, right? I'm not doing this thing where we say 2 to this power equals this. And that's just a quicker, faster way to get directly from here to the equation that you need to solve. So again, nothing wrong with this, but this is an alternative. Now for our last example, it says the cumulative box office revenue from the classic children's movie Finding Nemo can be modeled by the logarithmic function r of x, so r stands for revenue, is equal to 78.05 times the natural log of x plus 1 plus 114.3, where x is the number of weeks since the movie opened, and r of x is the revenue in millions of dollars. How many weeks after opening the movie was the cumulative revenue equal to 300 million? So in this question, they're asking, when is the revenue $300 million? So what they're asking is, when is r of x equal to 300? When does this occur? Well, r of x equals this thing. So to solve this equation, we need to know when is 78.05 times the natural log of x plus 1 plus 114.3, when is that going to be equal to 300? So now we just have a logarithmic equation. We can solve this first by subtracting 114.3. on both sides. When we do that, we get 78.05. Natural log of x plus 1 is equal to 185.7. Now to isolate the natural log here, I'm going to divide both sides by 78.05. This gives us the natural log of x plus 1 is equal to, and this decimal is pretty long, it's 2.379244,074. Now, when you're in the middle of solving a problem, you should never round numbers that you get in the process. So I should leave this exactly the way it is. We only round when we get to our final answer. So now to solve for x, we need to get rid of the natural log. So we're going to take e and raise it to the power natural log of x plus 1. And on the right-hand side, we have e to the power that you see here. Doing this allows us to cancel e to the natural log, and we end up getting x plus 1 is equal to 2.379244074. Oops, I'm sorry. We had to raise e to that power. Let's go ahead and calculate that. That's a mistake there. So we need to calculate what is this. Let's go ahead and plug that in. And so when we plug that in, we get 10.79673,824. And we can solve for x by subtracting 1 from both sides. And that, of course, gives us x equals 9.79673,824. Now, this is number of weeks, and they do say to round to the nearest whole number of weeks. So this is going to give us x is approximately 10 weeks. So in 10 weeks, the total revenue brought in from this movie was $300 million.